Hello students, I am Dr. Premlata Verma from Government Bilasa Girls PG College, Bilaspur, and today we shall be having a video lecture for MSc Semester 4, Paper 4, Fuzzy Sets and their applications. My today's topic is Compositional Rule of Inference and an example. This is a topic from Fuzzy Logic chapter. In classical logic, we have three types of inference rules which are based on various types of topologies. The first type of inference rule is called modus ponens. It is given by A and within bracket A implies B, bracket closed, and this implies B. Here A and A implies B. These two are called premises and this B, this is called conclusion. Similarly, the second inference rule is modus tollens. This is given by B bar, that is negation of B, and within bracket A implies B implies A bar. Here B bar and A implies B are premises and A bar is a conclusion. And third inference rule, hypothetical syllogism. This is given by A implies B and B implies C implies A implies C. Here A implies B and B implies C are premises and A implies C is a conclusion. Now we will be studying about fuzzy uh, everything. We are going to generalize all these things in fuzzy logic. So what we are going to do is that here the three inference rules, these are to be generalized. So let us come to the main topic. Students, many a times it is asked in the examination to write a short note on inference from conditional fuzzy propositions. So for this you must be prepared. So the notes is just for your reference. Inference rules is a classical logic. Inference rules in classical logic are based on the various tautologies. These inference rules can be generalized within the framework of fuzzy logic to facilitate approximate reasoning. The generalization of the three classical inference rules, which we have just learned, modus ponens, modus tollens, and hypothetical syllogism, are based on the so-called compositional rule of inference. So, thus, we have studied in classical logic that whenever we study classical logic, we write characteristic value of an element, and when we study in fuzzy sets, we write membership value of an element. So this thing I have written about the fuzzy sets. Before this, in classical sense, what we write, this b dash y as characteristic value of y in crisp set B. That is, we write B characteristic value of y, that is chi y in B. And similarly, here we write characteristic value of x in crisp set A. And here this is characteristic value of the ordered pair xy in the crisp relation R. So whatever here, this is just a generalization. Here what we write, this is membership. Membership value of y in the fuzzy set B dash. This is membership value of x in the fuzzy set A dash, and membership value of ordered pair xy in the fuzzy relation R. So B dash, what is B dash? B dash is a fuzzy set on universal set Y, and A dash is a fuzzy set on the universal set X. So thus, if A dash is a fuzzy set on X and R is a fuzzy relation on X cross Y, then we can find fuzzy set B dash on Y by b dash y is equal to supremum over x belonging to x minimum. This membership function can be written like this also, and this, and like this. We will write the membership function of an element x in the fuzzy set A dash by A dash x. We are not going to write mu. We will be using this formula. So b dash y is equal to supremum over x minimum A dash x comma rxy. And in matrix form, this equation can be written as b dash is equal to A dash o r. And this is called the compositional rule of inference, where r fuzzy relation is given by, in this I stands for implication, I within bracket ax by. So this was the generalization of the modus ponens in classical sense. So inference rule is in fuzzy logic, which is a generalized modus ponens, is expressed by the following schema. Rule is, if rounded x is A, then rounded y is B, and fact is rounded x is A dash, then the conclusion is in the form rounded y is B dash. It becomes the classical modus ponens when the sets are crisp, and A dash fuzzy set is equal to the crisp set A, and B dash fuzzy set is equal to the crisp set B. So while writing notes on modus ponens, you must write this expression also. Now, another inference rule in fuzzy logic, which is a generalization of modus tollens, is expressed by the following schema. Rule is, if rounded x is A, then rounded y is B. Fact, rounded y is B dash. Conclusion is x is A dash. In the previous one, what was written? What was given? Fuzzy set A, fuzzy set B, and A dash are given, and we have to conclude in the form of y is B dash. Here, what will be given? A and B will be given, and B dash will be given, and we have to have get a conclusion of the form x is A dash. So in this case, the compositional rule of inference, all the three compositional rules must be very well remembered. What is here? A dash x is equal to supremum over y minimum b dash y rxy, and in the previous case it was b dash y is equal to supremum over x minimum a dash x comma rxy. And this generalized modus ponens, it becomes the classical modus ponens when the sets are crisp and A dash is equal to A and B dash is equal to B. This we have already learned. Here, this is a generalization of modus tollens, and the compositional rule of inference has the form A dash x is equal to supremum over y minimum B dash y rxy when the sets are crisp and A dash is equal to A bar and B dash is equal to B bar, we obtain the classical modus tollens. And now the third inference rule is fuzzy logic, which is generalized hypothetical syllogism, is expressed by the following schema. Rule 1, if rounded x is A, then rounded y is B. Rule 2, if rounded y is B, then rounded z is C. Conclusion is of the form, if x is A, then z is C. In this case, rounded x, rounded y, and rounded z are variables taking values in sets x, y, and z respectively, and A, B, C are fuzzy sets on sets x, y, z respectively. For each conditional fuzzy proposition, there is a fuzzy relation determined for each x belonging to x, y belonging to y, and z belonging to z by the equations R1xy is equal to implication AXBY, R2YZ is equal to implication BYCZ, and R3XZ is equal to implication AXCZ. Given R1, R2, R3 obtained by these equations, we say that the generalized hypothetical syllogism holds if R3xz is equal to supremum over y minimum R1xy comma R2yz, which again expresses the compositional rule of inference. This equation may also be written in the matrix form as R3 is equal to R1 O R2. Students, based on this modus ponens, we have an example from the book of Clear, example 8.1. Similarly, you can find questions on modus tollens and hypothetical syllogism. I am giving only the solution of example 8.1. You can similarly try other examples also. Just you have to learn the inference rule. So the question is, let sets of values of variables x and y be x is equal to 3 elements, x1, x2, x3. Set y has 2 elements, y1 and y2. These are two sets, x and y respectively. Assume that a proposition, if x is A, then y is B. That means we are given with two fuzzy sets A and B on x and y respectively. A is a fuzzy set on x with membership 0.1, 1 and 0.6 for x1, x2, x3 respectively. And similarly, B is a fuzzy set on y with membership 1 and 0.4 for y1 and y2 respectively. Then given a fact expressed by the proposition rounded x is A, where A dash fuzzy set is given 0.6 by x1 plus 0.9 by x2 plus 0.7 by x3. These membership, in order to help me, please students, for my sake, you keep remembering that in A dash, x1, x2 and x3 have memberships 0.6, 0.9 and 0.7. Now the question is to derive a conclusion in the form y is B dash. Now, since we have to find B dash, that means it is a question of modus ponens. In order to derive a conclusion in the form y is B dash, we find B dash by the compositional rule of inference. This we have learned beforehand under modus ponens. You have to remember this expression. B dash y is equal to supremum over x minimum A dash x R x y. Now what is R? R is a relation on x cross y which is defined by Rxy is equal to I AXBY. And what is I? I is Lucas-Sievez implication. This in my previous lecture also I have told that you must remember Lucas-Sievez implication, which is given by IAB is equal to minimum 1 comma 1 minus A plus B. Or sometimes we also write 1 plus B minus A. Order does not matter. So what we have to do? We have to first, what is the expression from which we have to derive? Here, B dash y is equal to like this. A dash fuzzy set on x, it is given, and Rxy, the heart of the solution lies on the evaluation of this fuzzy relation R. So this fuzzy relation R is given by this IAXBY. So we will find fuzzy relation R. And before finding the fuzzy relation, we must first see, because this relation is will be a relation on x cross y. So x cross y Cartesian product, we have 3 elements in x and 2 elements in Y. Therefore, these ordered pairs x1, y1, x1, y2, and then x2, y1, x2, y2, x3, y1, x3, y2. This is the Cartesian product x cross y. Now what we have to find? We have to find fuzzy relation R. That means we have to find the we have to find the membership of each ordered pair in the fuzzy relation R. That means we will find the membership of x1, y1 in R, we will find membership of x1, y2 in fuzzy relation R, x2, y1. That means for all the 6 ordered pairs, we have to find the membership in fuzzy relation R. So let us start R x1, y1. This will be obtained from this equation 2. Rxy is given by I, Ax, By. So Rx1, y1 will be equal to I, Ax1, By1. Or what is Ax1? Ax1 is the membership of element x1 in fuzzy set A. And what is By1? It is the membership of y1 in fuzzy set B. This we have obtained 0.5 and 1, as you can see from the previous page. See, x1, y1. Membership of x1 in A is 0.5. Membership of y1 in B is 1. So 0.5 and 1. Now this is I 0.5, 1. And now we will obtain I 0.51 from equation 3. Put A is equal to 0.5 and B is equal to 1. Then we will get minimum 1. We have copied this. Minimum 1. 1 minus A. A is 0.5 and B is again 1. So this value is minimum 1, 1.5. This is equal to 1. So the membership of the ordered pair x1, y1 in the fuzzy relation R is 1. Now next, R x1, y2. This will be equal to I Ax1, By2. Again, we go to the 2 fuzzy sets A and B and find the membership of x1 in A and the membership of y2 in B. As we see, membership of x1 in A is 0.5 and membership of y2 in B is 0.4. Here, x1, y2. 0.5, 0.4. Again, from this equation 3, substituting the values of A and B, we will get 1, 1 minus 0.5 plus 0.4, and that is equal to 1. This is 0.9. We will get the minimum value, 0.9. Similarly, for all the other 4 ordered pairs, we can find the memberships in the fuzzy relation R. Students, you can easily calculate all these things. So for the 6 ordered pairs, we have got the membership value. Now, we have now obtained R. How this R is now known to us. This R is now known to us. Now, what we will calculate? B dash Y. That means the membership of every element of Y in B dash. Y has 2 elements, Y1 and Y2. So we will calculate B dash Y1 and B dash Y2. Now first let us write the fuzzy relation R in its full concept. Now this R, we have already calculated membership of x1, y1 in 1, x1, y2, x2, y1, x2, this is x1, sorry, x1, y1, x1, y2, x2, y1, x2, y2, x3, y1, x3, y2. So we have written this fuzzy relation in the form of a fuzzy set. Now we have to find the fuzzy set B dash, which is our main goal. So B dash, the formula B dash, inference rule, you know, B dash Y is equal to supremum X. This has come from this equation 1, this equation 1. So B dash y is equal to supremum over x minimum A dash x R x y. We have two elements in the universal set y, y1 and y2. So we will calculate B dash y1 and B dash y. B dash y1. So write y1 instead of y in this expression. We will get supremum x belonging to x minimum A dash x and R x y1 and x belongs to x. That means instead of y, we have written y1 throughout, and now x will now change. X belongs to x means x has three elements, x1, x2, x3. So what we are going to write, this supremum, we have instead of supremum, because this is a finite set, we will write here maximum. Maximum now pairs we will get for x belonging x is equal to x1, we will write minimum A dash x1 R x1 y1. Then again x2, for x take x2, so minimum A dash x2 R x2 y1. Then minimum A dash, instead of x you take x3, we will get minimum A dash x3 R x3 y1. You note that this membership is being calculated for y1. So throughout this expression, y1 will be there, only the elements of x will change, because here elements of x are changing. Y1 will remain the same. So we will get maximum. Now this minimum A dash x1, we had seen that A dash is equal to 0.6 by x1 plus 0.9 by x2 plus 0.7 by x3. I had previously told you that for my sake, you remember this. See, A dash 0.6 by x1, 0.9 by x2 and 0.7 by x3. So this is maximum, minimum. A dash x1 is 0.6 and R x1 y1, that means membership of x1 y1 in R, we have just now calculated. X1 y1 membership is 1. Here only you have to remember A dash and R. And from these two things, we will calculate B dash y. So minimum 0.6 and this is x1 y1 1, and A dash x2 this is 0.9 and R x2 y1, that means x2 y1 has membership 1 in the fuzzy relation R. Everything is coming from the fuzzy set A dash and fuzzy relation R. From those two points, yeah, you can substitute all the values. So similarly, Rx3y1, x3 is 0.7, A dash x3 is 0.7 and Rx3y1 is 1. So we get maximum, this minimum is 0.6, minimum is 0.9 and minimum is 0.7. This is equal to 0.9. Similarly, you can calculate B dash y2, that is supremum over x, minimum A dash x R x y2. And x will now change. How it will change? Once you substitute x1 instead of x, then you substitute x2 for x, and then you substitute x3 for x, y2 will remain the same. So maximum, minimum A dash x1 R x1 y2, minimum A dash x2 R x2 y2, minimum A dash x3 R x3 y2. This is equal to maximum, minimum A dash x1, as you remember it is 0.6, R x1 y2 you will get from this equation. From this you can substitute. Then minimum A dash x2 is 0.9, A dash x3 is 0.7, and you can substitute the value of Rx2 y2 and Rx3 y2, or by all such substitutions you will get maximum. Minimum 0.6, 0.9 is 0.6, minimum 0.9, 0.4 is 0.4, 0.7, 0.8, minimum is 0.7. The maximum of all these three is 0.7. Thus we have found the membership values of all the elements of the universal set Y in the fuzzy set B dash, because there were only two elements, y1 and y2. So we have obtained the fuzzy set B dash. Now B dash is equal to 0.9. Students, if it is not visible, I am just telling you 0.9. What is 0.9? It is the membership of Y1. So this is 0.9 by Y1. Now it is visible, and that 0.7 by Y2. And thus, from the modus ponens inference rule, we are able to get the fuzzy set B dash. Same from modus tollens also, there will be one example, example 8.2. Also, you can get find questions from the exercise. So students, such type of questions are very easy to solve. Now it is your homework that you solve the questions on modus tollens and hypothetical syllogism. Hope you may find my lecture to be helpful for your examination. Students, all the best for your exam, and this is the end of my lecture. Uh, thank you very much.